long time ago, a mentor of mine told me that machinists don't always make the best race car fabricators because we tend to make things fit too tightly. And I have just that situation over here. This is my 1966 International Scout rock crawler, and I started building this truck about 18 years ago, and a lot of things happened along the way. I never quite finished it. I've got a little bit of time, and I started working on it again now. But the problem I have is I made this snorkel, and it fits too tight. A snorkel is designed to take air for the engine in up high, and that way when you're crossing high water crossings, you're not sucking water into the engine. So this is designed to draw air into the engine. It goes down through the tube into a flexible hose and then on into the engine itself. What's unique about this truck is it has a fold down windshield. So there's a hinge here. The same hinge that the windshield uses, the hood shares. So there's no place for this to connect that doesn't interfere with the hood opening. I had to design this so that it would pivot out of the way. And so I made these saddles that attach to the roll cage, and this thing pivots out of the way. The problem is I didn't leave enough clearance, and I may have left, I don't know, probably 5/1000ths of clearance, but with that amount of clearance, you're only a coat or two of Krylon away from the thing not moving at all. So it's bound up, and you can see if I crack the saddle loose a little bit with my Allen wrench, now it rotates. Okay, so it would have to be like this in order for the hood to open, and then when it goes to there, there's a latch that locks it into position. So what we want to do is try to open these up, and I want to do some machining inside of these saddles, but it's a little tricky because some rocket surgeon went ahead and welded these on already. So we're going to have to get a little creative. Okay, so here we have the part on the healing bench, and as I said, this is something that was built 4 kids, 1 wife, and 2 houses ago. So it's been a while, and it's now that I'm finding time to work on the thing again, and I want to make it right. So we've got an issue. The paint buildup here closed down all the clearance I had. I didn't have enough clearance to begin with, and I want this to fit kind of loose, and I want to machine out this area. So because this has been welded onto here, you can't just take this part and put it in a lathe chuck. You know, we could assemble it if it was loose and put it in a lathe chuck and bore it out. We can't set this up in a mill and then bore it because the other one is down yonder. What we could do is we could set this whole thing up in a mill kind of like this, and then use a ball mill to go in and out of this shape and surface mill that bigger. Now, no one in their right mind would do it this way. Okay, so the theory is going to be to set the part up in a vise. This is the front view of the part. We have the x-axis going this way. We have the z-axis going this way. The tool orientation is going to be like this, and we're going to cut an arc. And we're going to step over and cut another arc. And because we're using a ball nose end mill, the part will receive a kind of a scallop shaped cut, and then we're going to step over just slightly and do another one and another one. And so in essence, we're carving out the whole shape of that part. Here's the center line of the sweep. Now, the 2 pieces are parted on that center line. So the radius would be dimensioned like this. Now, I measured the roll bar tubing, and we have a diameter on the roll bar of 1.755. It has a little bit of paint on it. For automotive stuff, we want it to be loose. We want it to slip and slide and move around and not bind. So we have to kind of get out of our machinist mindset for a little bit when we come up with the clearances that we want. I'm going to set this up, as I said, with like, let's go to 20 thousandths of clearance. Okay, so I'm going to add on to that 20 thousandths. So 1.775 is the final diameter that I want to end up with. So I'm going to figure out the radius for that amount. 1.775 divided by 2 is 0.8875. That is the radius value. So previously, we've cut a lot of arcs. I had always drawn the workpiece from the top view. And so we had the x-axis going this way, we had the y-axis going this way. We constructed our arcs on the xy plane. It was just the x and y axis moving in order to cut that arc. This is now different. We are going to be on a different plane. The x-axis goes this way, the z-axis goes this way, and we're going to cut our arc on that xz plane. Our control leaves us the flexibility to do this. Whether you knew it or not, all of the arcs that we cut in the past were cut in a condition that was called G17. And G17 makes all of your arcs lie flat on the X and Y plane. We have other options though. So where G17 is the XY plane, G18 is the XZ plane, and G19 is the YZ plane. Okay, so this arc falls flat on the X and Z plane. Again, the tool, it's a ball nose end mill, and it will be oriented just like that. So here's the center line of the tool, and it is going to be making an arc shape like that. So what we need to do is activate the G18 condition in our program. And once we've done that, it stays modal, and we will be cutting our arcs using X and Z commands. I want to use an end mill that has a diameter of 0.25. Okay, and we know that's going to result in a radius of 0.125. So let's not fool with cutter compensation. Let's just figure out mathematically what the arc is at the center line of the tool, and program that. Try to keep this real simple. Therefore, when I qualify the tool, I'm going to be tricky. I am not going to qualify the tool for the tip, but I'm actually going to qualify the tool for the center of the radius of the ball on the end of it. All right, and so therefore, we're programming this arc that I have in this dotted red line. The question now is, what is that radius? Because that's the radius that we're cutting. So what I have to do is take my 8875 and subtract 125 from it. And I got 762 and a half thousandths. That's the radius that we're cutting through that arc. Okay, so we know the R value for the program. What we now need to determine is what is the start position and what is the end position for that arc. The start position is going to be relative to an origin. So we have to determine now, where are we going to place the origin on this part? I could put it smack in the middle. That would probably be logical. I could put it really anywhere I want, but by placing it in the middle, if this is truly symmetrical, which it is, my math calculations are going to be easy. It's just going to be the positive and negative signs that are changing in my numbers. So from here, if this is the origin, to here, here to here, is a distance of whatever the radius is, which would be 0.7625. Now this is in the negative direction. And from here to here is also 0.7625, but now in the positive direction. So that is where the center line of the ball of the tool will be parked prior to starting the arc. We will cut an arc at a radius of 762.5 thousandths, and we're going to end up there at positive 762.5 thousandths in the X. The R value that we program is going to be that number right there. And the other thing we need to now consider is, where is the y-axis? So this is us looking at the front of the part. Let's look at the shape of the part from the top down. So here is, well, here's where that arc starts, here's where that arc ends. Looking from the top down, I am going to place the origin, whoops, not there. We're on the center line. I'm going to place the origin right here. So I'm going to place it with y0 on the front edge of the part. So this is going to be the y-axis, and this is going to be the x-axis, and y0 is going to be right here. Okay, so what we're looking at here, viewed from the top, would have the ball mill placed right there. Okay, and it's going to begin here, and it's going to dip in and cut that arc right like that. Viewed from this way, it's going to dip in and cut the arc like that. Okay, so the top view, front view. So let's get the programming. Later on, I just point this out, later on after we do this simple cut across here, I'm going to do another cut that is going to produce a relief in here so that I can put that plastic band in there that I was describing. Obviously, you probably figured out that that 20 thousandths of clearance doesn't allow for very much plastic. So the cut that we're talking about right now is just going to give clearance on the metal. Once I lay the plastic in there, it's going to protrude, and all of the contact is going to occur plastic on metal. So we don't have any metal on metal contact. Okay, that's down the road. Let's keep it simple. Let's just talk about cutting this one arc, and then how we can translate those arcs across here, stepping over all of the way. All right, so we're going to begin the program. Just throw some numbers in here. We're going to transition from the program number right into the safe start codes. So I'll throw a G20 in there. I'll throw a G40 in there. I don't want a G17 this time. Remember, I want a G18 for my XY plane. Actually, let's hold off on that. We'll call that code later on. I don't want that one yet. G94 for inch per minute, and G80 cancel any can cycles that would be active. That's good enough. Now we're going to do a tool change. Let's say that T2 is a 1/4 inch ball mill. going to, after the tool change, go into G0, go into G90, and we're going to park ourselves at that first position. So right here, what are the coordinates for this position? Well, the y is going to be at 0. So let's go ahead and throw that in. And the x, we said if this is the origin, x is negative 762.5. Okay? At this point, the machine still doesn't know how long the tool is. So we're going to call our G43 height offset call, H value 2, which matches the tool number. We're going to bring our Z down to clearance plane. Now, this is going to be a rapid condition. Right? We're still in rapid from the previous block. I don't want to come down below Z0 with the tool in rapid. I would rather have the tool up here and then feed to depth. So I also want you to keep your head wrapped around the fact that we've qualified the tool to the center. We are programming the center of that ball. So we have 125 thousandths of tool hanging down below whatever we're commanding the Z position of the tool to be. So that means that if I wanted 100 thousandths of clearance between the bottom of the tool and the top of the part, I would have to take that 100 thousandths and add the 125 on because I have that much more tool to adjust for. In other words, I would go to Z.225 and that would yield 100 thousandths of clearance here. Now I'm going to start my spindle. Let's just say 3,000 RPM, and we give it an M3. We'll throw an M8 coolant command in the next block. And now I'm going to call the G18 command. This switches us to the XZ plane on which we want to cut the arc. And we are going to cut from here to here, G2. Sorry. Cut G3. And the X is going to end up here. That X position is 0.7625. And the Y position isn't going to be even in this. It's not moving in the Y. And it's ending back at Z0. And then finally we call the R value of the radius that we're cutting, which is 0.7625. And that will cut an arc, not in the XY direction, but in the X and Z direction. So, looking at it in this view, we would have made one cut like that. What I want to do is now do the same thing, but I want to step over and do it again. And you know there's going to be a little bit of a, what we call a cusp height in between here. It's going to kind of look like waves on an ocean. When you have a ball mill and it's cutting into the part like that, and then you step the ball mill over and you make another cut and another cut and another cut, these little ripples here are called cusps. And the closer together our step over is, the shorter the cusps are and the finer it is. For something that you want to spend a little bit of time doing handwork on, polishing it out with a abrasive cloth, you can get away with a little more cusp height. If you're doing a very complex surface milling operation in like a mold cavity, you would want those cusps to be very small so that you don't have to do a lot of polishing work on it. What I'm going to do is I'm going to step over 50 thousandths for each one. Now, the other thing I should mention, if the ball mill is a bigger radius, the cusp becomes shorter for a given step over amount because the flatter of the curve on that ball. All right, so we've cut our one arc. what I want to do now is I want to step over 50 thousandths, and I want to do it again. So, my Y is going to be told to go, and by the way, I need to go back to a G0. Well, let's build a little bit of safety in. Let's go G0, and we're going to pull the Z up to 0.225. You know what, I just noticed something. I never took my Z and brought it down to Z0 to start the arc. I'm going to remove this M8 command, and I'm going to fix my program because I made a mistake. This should have been a G1, and I should have commanded Z to go to 0, and I should have given it a desired feed rate. So, my bad. All right, so this told the Z to go to 0, which placed the center of the sphere at 0, and then the next command was the G3 to here. I'm going to then give it a G0 to Z positive 255, and that's going to bring the tool back up to clearance. Now we're above the part by 100 thousandths. In the next block, I'm going to make my Y step over. So I'm in a G0, I'm above the part, so I'm going to just tell my Y to go positive 50 thousandths. And I'm also going to tell it to return back to the start position. All right, so let's do a separate move for that one. I'm going to go to X negative 0.7625 and Y position of Y0, just like I did for the first arc. This is where I started from. And then I'm going to command my G1, and I'm going to take my Z down to the negative 225 thousandths. That's not right. Sorry. My Z is going to go to 0. Okay. So we ought to see kind of like a routine here, a pattern. We've gone to the start position. We've taken our Z to clearance. And then we fed our Z down to 0 to cut the arc. So here we've gone to clearance position. We've moved our Y to step over. We've gone to where we're going to start the arc. And we take our Z down to the start position. Now we're going to cut the arc again. In order to make this simple, or easy to write, I should say, I'm going to create a package here, and I'm going to copy it and paste it. Because I'm going to be stepping over a whole lot of times in order to get across that part. The part is 5/8 thick, and I'm making 50,000 step over, so I have to do this 13 times. So to save a little bit of effort here with the writing, I am going to do a little trick where this Y step over, I'm going to put in a G91, which is an incremental command. And then I'm going to go right back to G90, absolute, to go to my absolute position to start the arc. Okay? That way, if I were to take this whole area, copy it, and paste it, all the instructions will be built in, and I did not have to modify my Y positioning move for every time it cuts an arc. In other words, it's going to make an incremental shift of 50 thousandths every time it cuts. And it's going to shift up positive 50 and positive 50 and positive 50 across the part in the Y direction. But all the other codes are going to stay in an absolute position and reference the absolute origin. So I'm just swapping into incremental just for this Y position. And then I'm going right back into absolute. So by grabbing this, copying it, and pasting it over and over again, 13 times, I can move across that part and I can cut that. And we're going to do that on the simulator. Now I know Alex is probably twitching right now because he'd love to incorporate macro programming here. This is a perfect place to do it. But I want to keep this light. I want to focus on just the fact that we're cutting this arc on the XZ plane and the fact that we're stepping over and doing surface milling. I think later on we're going to take this and retrofit it with a macro so that it does a loop, and you'll see how we can simplify this even more. In fact, if we use the macro, instead of copying this and pasting it 12 more times, we would just have to write a few blocks of code, and it would build automation into the program where it would step over all the way across the part until it reached its destination. So next we're going to take this and we're going to throw it into a simulator, and we're going to see if it does what we expect it to do. Okay, so here we are on the simulator. All of the code that I had written on the whiteboard, I have now put into the simulator, and we're going to let it rip and see what happens. On the screen, you can see that's what the front of the part looks like, and here's the top, and here's a isometric view. I'm going to rotate this around so we can get a good idea, and I'm going to step down through the code. Here we are going from a Z position of 0.225 that we spoke about to Z0. All right, and you can see the cutter position is the end of this arrowhead. We switch into G18. Next, we are going to do our G2. G3 went the wrong way, so I put a G2 in and it worked correct. When we get out on the mill, we'll verify that that's right. Here it goes to the X positive endpoint that we specified, and back to Z0 at the correct radius value. So that move takes us from here to here through that arc. Next, we do the G0 move that brings us back up to the clearance plane, and we have a color-coded red movement here. That is for a rapid. So the green is going to be a feed move, the red is going to be rapid. We're back up above the part after the completion of that one arc, and then we do our incremental. We go to the G91, and the Y movement shifts over by 50 thousandths. And then in the next move, we're going back to absolute. So we go to absolute mode again, and we're going to move back across the part to X 0.7625 in the negative. Now, when I wrote this on the whiteboard, I had accidentally written a Y0 in here. That was no good, because what that would end up doing is, because we've gone back into absolute, this would put us at Y absolute 0. And so looking at that from the top, that brings us, after we make that 50,000 shift move, it brings us back to Y0, which would put us in position to repeat precisely the same arc we did the first time. That's not what we want. We want to get rid of that, and in doing so, it's going to keep the Y where it was placed under incremental, and then the only thing that's going to happen next is it's going to move the X back to where we want to start the next arc. Okay, so I eliminated the Y0 movement from this block. This puts us right back to the start position. Okay, and then in the next block, the Z drops down to where it needs to begin the arc from. Okay, so let me take you through this again, step by step. Down to the start position of the arc, cut the arc, retract the cutter, shift over 50 thousandths, go back to where the arc begins, go down to where the next arc is to start from. Now, think of this as a package, and I've put these little flag headers in here so that you know this is where that surfacing cut starts, and this is where the surfacing cut ends. We are going to take this package in its entirety,
and I'm going to copy it, and then I'm going to place another one, and let's see what happens. Because the way that we wrote that, because we had it do a incremental shift over, it shifts over 50 thousandths, and then it will do it again. So looking at this from the top, this right here is representing the first arc. It shifted over, it represents the second arc, and then it positions for the third. Okay, so that's what it would look like from the front. From the right side, we see the first arc, the second arc, and then we're in position for the third arc. And that's what it looks like if we sweep it around. So we can do the same thing. We can paste that package again, and now we get another arc. So we've completed 3 arcs at this point. I said that we needed to do a total of 13. So if I hit enter and I paste it, enter, pasted, that's 3, 4, 5, 6, 7, 8, 9, 10. We ought to have all of the arcs that will get us across the part. Okay, so looking down from the top, you can see those. We'll count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 arcs. At the conclusion of the last arc, it carries the cutter back to the beginning. Let's see if I can roll this around so you can see it. It carries the cutter back to the beginning, but it does not make one more arc. It just stops. Here it is. So this is where it feeds down to position for that final arc, but it never cuts it. So at that point, at the end of where we've done that pasting move, all we would have to do is then end the program. So, you know, we throw a G28, G91, and we take our Z home to Z0, and then maybe we wanted to do G28, G91, and we can bring our Y to 0. That would bring the table towards the operator, and then we could end with an M30. That would do everything that we want it to do. All right, so I'm going to go File, Save, and that is how using copy and paste in an editor can get the job done. Now, this is lengthy. This program's kind of long. It was pretty easy to use the copy and paste button. Anyone can do that. However, it's a little tough to decipher maybe, and here's the big problem. Let's say we cut this and we are not happy with the dimension that we get, and we wanted to make it just a little bit different. So we go in here and we have to edit our start position, our radius value, our end position, our reposition move. That only works for one of those iterations. We'd have to do all of that adjustment to this iteration and this iteration. 13 times we'd have to make changes. So what I'm going to teach you next is how we can condense this into a package, but not use copy and paste, but use the automation built within the machine in order to duplicate those iterations over and over again at new locations. We have the core of the program written. All we have to do is add the trickery to make that happen, and it's not too tough. So we will in next video, we will be modifying this code, producing the same results in the simulation and on the machine, but ultimately it's going to be a cleaner, simpler program, and it's easier to edit. And we are going to run this part in the machine, and we'll see what happens and see if it works in real life.